Welcome. So today in this particular lecture, what we will be doing is to understand what we do exactly for one of the cases of spatiotemporal deep learning. Now, in the earlier lecture, what I had you guys introduced onto was to understand videos as a tensor and the difference of how do you convert down all of these video frame when you have color video acquisitions, and what is the tensor dimensionality and priorities in terms of the arrangement for handling it out. Now, one thing which was clear is that the meaning and interpretation of channels is quite different when we are writing out these tensors, and in fact what you would effectively have is, if you have a spatial dimension and the temporal dimension, then for each of the color channels you have that packed down in terms of its own 3D tensor, and the whole resultant is a 4D tensor which comes out. And in the subsequent lecture we had studied about another newer kind of a neural network called as recurrent neural network, which typically deals on the aspect of recurrence, or if I have some sort of a dependency of my current state on the previous state as well as the input of the current state, then these kind of networks are what are called as recurrent neural networks. And typically what we studied was a modern variant of these RNN called as the LSTM, or long short term memory. The advantage was that you could get down short term or very recent past kind of behaviors modeled out quite easily, and the other one was that you could also retain down long order relationships in terms of your temporal dimension. Now, this did have a very significant advantage. So, one of these was that initially they had come up for natural language processing and for grammars and auto translate, auto completion kind of works, but subsequently when people did realize its great advantage, we started using these for video analytics as well. So, today's example is just to give you again a basic very brief revision of what we had done, so that you have all the context set down, and then I would enter into one of these case studies. So, we have two specific case studies and both of them are spatiotemporal deep learning. So, in one of these examples is where we are going to use a recurrent neural network, and we see how the performance comes out, and the other one is, if in case I am not trying to use a recurrent neural network, then how will I be modeling out the whole network over there. So, I would be showing you both of these examples, and then that is how we keep on proceeding. So, on the organization side of it, there is a basic revision of the concepts once again, and then I would enter into the spatiotemporal deep learning. So, in the last lecture where I was introducing you to this whole concept, we did a very fast walkthrough, and then I set down that there is another aspect of recurrent model which we would be doing in the subsequent one. So, now that you know about how recurrent neural networks work, as well as how the whole spatial data can now be processed and brought down into a lower dimensional tensor space on the temporal side of it, we are going to review that and come down to an actual model where we made use of it. Now, there is a case study which we will do for surgical tool classification. So, this is a very specific one from medical use cases, and one of the publications which we had in CVPR 2017. So, we will open up the paper as well and go through some of these stages inside over there to explain you what is a practical design problem which we had faced and how we thought of overcoming, and what were the solutions which we achieved out of it. And then we would enter into spatiotemporal deep learning without RNN as one of the case studies for a student project which we had done, where without using these LSTMs can we still end up doing. So, can there be a fully convolutional network equivalent for analyzing out videos as well. Now, a very basic introduction, just a briefing of it. So, if you had your images as such of m cross n, and it was a 3 channel, you had a 3 cross m cross n, and then your convolution kernel was also a 3D kernel which had number of channels equal to the number of channels in the input image over there, and it was 3 cross w cross h. And then when you convolve it out, you have your resultant. But then in case of a video, what happens is that your frame dimension is still m cross n, but then you also have another component of time over there, and each frame is a 3 cross m cross n. So, your resultant is t cross 3 cross m cross n. Now, when we get down into the video organization in terms of a tensor, what we need to do is that you have your overall organization given down as t cross 3 cross m cross n, where 3 is the number of channels. Now, these number of channels can keep on varying, so they not necessarily need to be 3, since we are dealing with RGB color images. So, we still have this option of having just 3 channels over there, but that can be different based on whatever is the output from your previous stage. Now, the only issue is it is not easy to handle it down in that way, because number of channels is a unique quantity over there. Now, what we can do in that case is we can break it down into a red a spatiotemporal tensor which is T cross M cross N for the red channel. We break it down for the green channel, and similarly we break it down for the blue channel as well. So, once we have these kind of representation coming down over there, then each channel itself is T cross M cross N, and since there are 3 channels of T cross M cross N, so this whole tensor is now a 4D tensor of 3 cross T cross M cross N. Okay. And if we enter into a convolutional network for this video handling, then what we would end up having is that you have a 3D volume of T cross M cross N for the red channel, green channel and blue channel. Next we are going to convolve it down with the convolution kernel, which is also 3D in size. Now you have this 4D collection. So this is just a bucket on the 4D space over there. Each of these kernels is a 3D kernel. So you have one kernel for the red channel, one for the green channel, one for the blue channel, and this together does a dot product, and for every point in this volume you are going to get down one output point over here. Okay. And so this convolution is going to be on by giving you strides along the x, along the y, as well as along the t dimension over there. So the resultant is also a 3D volume, it is not a 2D planar matrix in any way. Now if I have multiple number of these kernels, then they are going to define one output volume for me, and that corresponds to one output channel. So your input was a 3 channel input, you had 4 such convolution kernels over here. So your output has a 4 channel output over there, and everything is a 3D volume which comes out. So this was clear for us. The challenge however was that when you are trying to do this kind of convolution using video tensor, then your total output size has this kind of a relationship which comes down, and the challenge which it actually poses is the data issue over there. Because the moment you have this massive amount of convolution coming down and the resultant, so the size of this resultant is something which is guided down by m minus w plus 2p divided by s plus 1. Now this padding along temporal will also be guided down over there. So we are taking only along one of these axes. So if you take along all the 3 axes, then you get down a similar resultant coming down. So as a typical case, what we had done in the last class was if we take down that m equal to n equal to 2 to 4, and w is equal to 3, and pw is equal to 0, and sw is equal to 1. In that case we get down our OW is equal to 2 to 2. Okay. Now if we take an input of this form which has 3 channels, and on the time stamping on the time axis over there, there are 100 time axes over there, and the spatial size is 224 cross 224. Now if my convolution is there with 16 such channels coming down over there, each of size 3 cross 3 cross 3, then my output comes down as 16 cross 98 cross 222 cross 222. Now if you look down at this particular aspect, now this output volume is almost 5 times more bulky than the input volume, though we had just lost down by a reduction of 2 pixels on the time axis, 2 on the width and 2 on the height. Eventually there was an increase in the total number of channels on the output, and that is about 5 times more, and this is the challenge which we are facing. And what we said at that point of time is, let us move over to other concept which is called as spatiotemporal deep learning, such that I can now consider my frames individually and then reduce it down to some sort of a feature space, a 1D tensor feature space over there, such that frame at a different point of time is what can consolidatedly be represented in terms of just a 1D tensor, and that can in some way help me in solving this problem. So now what happens in that case is that you have your video which has t cross 3 cross m cross n frames over there. Now what I do is I take only one frame at a time from one particular instance of t. Now I take one of these frames and I pass it down through one of my neural networks over there, and then I get down my output tensor which comes over there. Now this output tensor is of size k cross t which comes out. So essentially now if I use another kind of a concept of recurrent neural network standing at that point, then I should be able to use those features as input to it. Now this is what we are going to exactly do in this example over here from one of the case studies. So, this is from our publication at Division Workshop in CVPR 2017, and the objective over here, what you see in this video is basically so it's captioned out as a surgical video. So, this is an endoscopic surgery. So, it's a form of minimally invasive surgery where you just drill a small keyhole into your body, and then through this keyhole there are small surgical tools which are very thin. So, they are almost like the size of a refill of one of your ballpoint pens. So, that is what enters, and there can be multiple tools. So, some of these are so you see some sort of a pinching tool over here or a grasper. You see some of these which are just ablating out over here. So, they are hook like tools over there. So, let us play that video again. And there is a surgical operation which is going down. So, these are typically carried down within the gastric cavity or for operating down on your liver tissue, and this is being carried down in the gastrointestinal cavity as seen over here. Now, the whole objective behind doing this was that we have these different kind of tools. There can be multiple tools, 2 or 3 tools at a time which come down. So, can we identify those tools over there in some mechanism? So, that was the whole objective. Now, one way is that you can typically say that I have one frame, and then I can process this frame and get down a classifier ready as a multi-hot classification. So, it is not necessarily that you will have only one class coming up over there as the result, but you can have multiple classes also coming up. Now, what we realized eventually was that there within certain frames there can be discontinuities, and you can obviously increase down on the total performance if you are trying to have some mechanism of incorporating and learning the spatial continuity between features which come down in a frame. Now, being able to learn down the spatial continuity between features which come down in a frame would enable you to actually have a good grasp over what is the possible tool which is present over there, even if it is vanishing out for 1 frame or 2 frame, or there are misinterpretations on if you are trying to classify it on a frame basis, then still this long term context on the temporal side of it is what can solve it out, and that is what we solved out over here using a temporal problem. Plus, on top of it, there is another extension of this work which we had done, and that was more of to classify different phases of a surgery, or that is the kind of action which is taking place in this video. So, in the lab sessions, what we will do is we will be taking down another standard video data set, and where we will have to classify down the different actions. So, it is going to be an exercise which all of us are going to collaboratively solve over there, and find out which of the mechanism works out pretty good. Now, here the whole idea based on what we had seen in the earlier slide. So, what we do is we extract out the frames over there. So, now each of your frame is a 3 cross m cross n. Okay. Now, for our work over here, we needed to have so what our idea was to get down a pre-trained network, a very standard pre-trained network which works out on ImageNet scale resolution. So, that also meant that these frames will now have to be resized to fit down the 224 cross 224 image size for any of the work with ImageNet. So, that is the next step which is done. Now, you can see over here that on these frames over, so some of these boundaries are quite blanked out, and the reason is quite simple. You have a camera which is placed on top of a circular aperture of a lens, and this lens is a optically guided lens within the body cavity. Now, since the camera sits on top of it, and this is done in an arrangement so that you do not miss out on any of the information which comes out from the circular aperture. So, the camera is placed out in a way and such that this image is a small region within it. So, that is what you exactly see within the slide. Now, we can actually chop off these extra perimeter parts over there, these peripheral black parts. So, they are just truncated off, and then you near about have a square frame which there might be some sort of a squeezing needed at point of time, but nonetheless that does not introduce much of distortions as we had seen while processing it out. Now that you have your frames which are resized and cropped down to come down to your ImageNet scale resolution, now you can take down any kind of a standard model over there. So, you can try out with the VGJ net, you can take an AlexNet, you can take a residual network, you can take a Inception net, Inception V3 or the Google net, you can take a densely connected residual network, any of them are going to work now. Now, once you pass it through it, then you are going to get down this final layer of features. Now, in the domain adaptation lectures and the domain adaptation practicals which we were doing. So, what we had done is you had seen that we do a forward pass over there, and then the features are collected, and somewhere at the last layer which is just the classification layer, you truncate out instead of 1000 layers we were putting down our 10 class classification. So you just had 10 neurons instead of 1000 neurons on the final one. Now here the idea is quite similar. So you can truncate off the last classification layer which had those 1000 neurons over there, but then you don't connect it to any further smaller number of neurons, you just retain that over there. So in case of your VGGenerate or something, you are going to get down 4096 neurons over there. Now if you come down to say a residual network, you get down just 512 neurons over there. Now this is your tensor which represents the spatial characteristic at one point of time. However, you are going to have these kind of tensors at different point of time. So corresponding to each frame, you have one of these 1D tensor which comes out over there, and then you stack this whole thing. So this is stacked along the time axis. This is not stacked along the x or the y axis over here. It's stacked along the time axis. So on the x axis you have a dimension of 1, on the y axis you have the dimension equal to say 4096 or 512, and then along the third axis or the time axis you have the time dimension going down. Now once you have these sequences available over here, so they can be fed down to your LSTM as features. Okay. Now obviously at the start point over there we don't have the option of a previous state coming down over here. So anytime which we do, what we do is we typically take a bunch of frames over there, and then the last frame is whose state we try to predict out. Now the previous frames are what just go as information over there. Nonetheless, but training for this one, what we do is since you have multiple modes of training a LSTM over there, so you can have a many to one, you can have a one to many, you can have a many to one, a many to many, these kind of notifications. So we train it down as a many to many. So given that you have n number of frames which are given as the input in terms of features, you will be trying to classify all the n frames over there as a sequence of outputs. So the class labels on all the frames are what are labeled out and then chunked out from the LSTM. Having said that, what we more importantly put down is, now that you have this time stamping for each of so classification label for each of the timestamps available to you, we don't consider all of them. So we formulate this as a moving window kind of an approach, or something which is a time invariant approach, in which provided certain frames have come down, we are going to predict down only what is my current frames classification label over there. So if I am currently at the 100th frame and I have a temporal length of say 5, then I am going to use my frame number 100, frame number 99, 98, 97, 96. So all of these 5 frames over there, and now my LSTM is going to give me an output of classification for each of the 5 frames, but then I don't use the frame classification from frame number 96 to frame number 99. So instead I will just be using the classification for frame number 100 and just give a result. So at any point of time, what this method would necessarily need you to do is, even when you are training or testing over there, you chunk in a block of frames, but then this block of frame has to be contiguous, and whichever is the recent most frame over there. So the previous frames classifications are not taken, only the current frames classification is what is taken down. So that's going to give you one single scalar output for a current time frame based on whatever has happened in the previous few frames over there. Now once you do that, this is what we were predicting out. So there were these multiple tool classes present over there. So on top there is something which is for the video activity classification, which is also called as phase classification problems for these kind of videos. Now here the whole idea is you see this probability bar graphs coming down over there. Now whenever there is a new tool which comes in, so there is a grasper which comes in and then goes out. So whenever there was this grasper coming down, you could see that one, and then when it's out over there, you see there is no tool present. So that's what it's showing down. And all of these predictions are just for that current frame. There is not a whole sequence of frames on which it's trying to predict it down. Now on the other side, on this top, you have these phases of surgery. Now this is the current phase of surgery which it is showing. Now it also shows a possibility of the next phase and which may come up, and that's an extension of this one. What we do is, since there is temporal context modeling down over there, there is a different field of sequence modeling called as hidden Markov models or Markovian field processes. So what they do is, based on how many things have occurred in the past, it can try to predict what may be a possible outcome in the future. So that's what's going on over here as such. Now nonetheless, we are just concerned about this first part, which is to find out which is the kind of a tool which is present over there, or just the activity, current activity stage, not to look into the subsequent one. So that's not part of the syllabus over here. So in the classroom exercises what we will be doing is with one of them. We are going to have your example tutorials ready, in which in the next class, where you are going to get down a set of videos over there, and you would just be classifying what is the activity shown down in that video over there. Okay. Now, this is one part where you have your spatial CNN working down, and then you have your features extracted, and based on the features you are going to feed it down to an LSTM and then classify it out. Now, there is also another kind of a problem. So, this is what we had done with goal directed human videos, and here the idea was that you can extract out these frames over there and do the same kind of a modification as in cropping and then resizing it to 224 cross 224, and then you feed all of them onto CNN for extracting out features. Now, once your features are extracted out, the whole idea was that can we have these at multiple time frames and then draw a fully connected neural network and then do a classification. So, here it was just 4 different classes which needed to be classified, and what we had was we start with one of these frames at whatever level. So, say this is at the tth frame, then I go back and take all the previous 4 frames. So, t minus 1, t minus 2, t minus 3, t minus 4. So, this has a temporal context window of 5 frames available to me. Now, stacking down all the neurons together in a linearized fashion, I do a fully connection to the next layer which has 4096 neurons. Now, this is dependent on you can pretty much choose down and work out which would be a good combination of having the total number of neurons over there, and then from there I connect it down for my classification. Now, what you see is that only common denominator is the spatial features which you can extract out from these CNNs, but then the rest of the temporal modeling is now a fully connected modeling over there. So, this particular kind of a model has a certain kind of a disadvantage, because even long order neurons and frames of activities in which have occurred much earlier, they are also given a similar kind of a preference, and everything is given down a similar preference and coming up over there. The network has to actually learn down over there. The other downside is that the total number of weights which this whole network has to learn is much higher than what would happen down within an LSTM. So, the network is definitely much more cumbersome. However, the good side is that you can now use just a fully connected network and try to do it out. Now, what we have is on the green you have the ground truth, which is the actual class of activity which is going on, which is predicted, and on the red you have the actual predicted class which is coming out of this particular example of a spatiotemporal deep learning. Okay. Now, these are 2 examples over there of how you can solve it out. There are still much more problems over there. Now, if we get back onto trying to understand some of these predominant problems, then I would definitely refer you to this particular paper which we had published out in CVPR in 2017. Now, here the overall idea was to get these kind of classifications done down for whatever tool is present over there. Nonetheless, what we realized is that training these networks over such grossly newer kind of data is not so easy, and more than often these videos are quite biased towards a certain class over there. Now, let us look into the organization over here of this bias. Now, if you look into this figure over here on 6A, and then the other one is on 6B. So, this is a particular kind of a dependence graph which we see over there. Now, some of these frames have multiple tools, you do not have just one tool, and some of these frames have just one tool. So, some frames can have 2 tools, some can have 3 tools, and there are 7 different types of tools out of which these can come up. Now, whenever you see these codependencies, say on these frames over here, there are few frames which have this kind of a tool, grasper as well as clipper and bipolar. Okay. There are some of them which have a grasper as well as a specimen bag present down together. There are some which have a scissor and a grasper present down together. Now, this does make it really challenging, and you would see that majority of your frames are just grasper, hook and clipper, and all the other ones, other 4 categories over there are much lesser. Now, technically your network would tend to be heavily biased towards these particular classes, and then it would underperform on these classes. Now, for that you need to balance it out, and a balanced data set is something which would be looking down over here. So, this is a extra investment which you have to do. So, there is no neural network or a learning algorithm in order to sample out from the data and actually create a balanced out data set. Now, that is something you have to do, but the method is not so hard. though there is a lot of human intervention required over there. So, what I would suggest is that you can actually go down through this particular paper and on to understanding the design aspects and what are the challenges which you would be facing down. Now, the code is also available for this particular work, but it's not based on PyTorch, it's on the earlier version of the library called as Torch over there. Now, we had run down multiple experiments over there, including different kind of networks. So, we had tried down spatial feature extraction with AlexNet, GoogleNet and ResNet, and then there was one where you don't have any LSTM working, you just try to classify the tool in a frame based on what is present on that frame. So, it is a frame level classification. The other one is where you also have a temporal context modeling set down with using a LSTM for your recurrent modeling. So, in together what comes out is an interesting aspect over here. So, these are for different baselines, and this is a full comparison over there. So, for each of these baselines is what is mentioned out over here, and this was the model which we finally used for getting the maximum accuracy, and this is where you have a ResNet 50 plus an LSTM coming down together in order to give you the highest accuracy per class and highest accuracy overall as well. So, you can also have a quick look at the video over here, which is on YouTube, and these are few frames which were wrongly interpreted, and it was always found out that there is no surety on which frame will be wrongly interpreted. It heavily depends on what networks you are using, and that is more of because every network tends to learn down a different kind of a feature and attribute over there. So, having said that, this is where we come to an end on understanding temporal deep learning and spatiotemporal deep learning onto a major context. So, in the next two lectures, we will be doing a hands-on with that one, and that would come to a closure of our course. So, this is the last week of the course, and I wish you all the best for your exams as well subsequently. Thank you.